In the first installment, we discussed fundamentals of trigonometry, focusing on sine, cosine, and tangent. Here we're going to use those concepts to solve a physics problem. We have a 100-pound stoplight suspended from two cables, one on the right, one on the left. The one on the right makes an angle of 60 degrees with the horizontal. The one on the left makes an angle of 40 degrees with the horizontal. We want to know the tension in each cable. Well, the gravitational force is pulling down on the stoplight with a force of 100 pounds. That's the definition of weight. Weight is the magnitude of the gravitational force. The stoplight is still hanging there. So the cables are holding it up. The vertical component of the cables must add to 100 pounds. So let's draw a force diagram. Those are the forces. Gravitational force down, two tensions at some angle. What we'd like to be able to do is get the upward components, because we know those add to 100. TL plus TR isn't anything. The vertical components must add to 100 pounds. Further, we know that the sideways components, TR is pulling to the right and TL is pulling to the left. Those have to balance because it's just hanging there. So let's put these components on the force diagram. So there's TR in the y direction, vertically. TL in the y direction, those have to add to 100 pounds. And TRX, the horizontal, must balance the horizontal of TLX. They're in opposite directions, the force has to be the same magnitude. Now if you look at those things, you say, oh man, I think I see a triangle there. So we need a way to relate the components to the vector and the angle it makes with those components. That's what trigonometry is for. So the sine function gives us the length, even though this is a force, we're going to call it a length. TRY divided by TR is the definition of sine. So sine 60 is the opposite over the hypotenuse. We can solve this for TR sub y by multiplying both sides by TR, and we have this expression. The vertical component related to the magnitude of that vector, the hypotenuse times sine 60. And we can do the same thing for the other four components. Cosine 60 is TR sub x divided by TR. And we can solve that for TRX. And for the cable on the left, we can do the same thing. TLX is TL cosine 40. TLY is TL sine 40. So we should probably get rid of the tensions because these aren't two forces. It's either the tension force or its components. So let's get rid of those. And we can substitute the trigonometric expressions that we just calculated for each of those components. So TRY is TR sine theta, TRX is TR cosine theta, TLX is TL cosine 40, and TLY is TL sine 40. We are on our way, carefully, inexorably working towards the answer. Because we invested the time to make a good force diagram, we can just look at it and say, well, TL sine 40 plus TR sine 60 must be 100 pounds. It's holding up the stoplight. That's what's holding up the stoplight. Further, in the other direction, the horizontal direction, they have to balance. If they didn't balance, it would be accelerating. So in the horizontal direction, we can write TR cosine 60 equals TL cosine 40. Now we have two equations and two unknowns, and we have to do some math. Be careful and grind it out. So here are our two equations, and there's numerous ways to do this. We're going to solve for TR using the bottom equation by dividing by cosine 60. A lot of algebra here. You have to be careful. So that's TR. We have this expression for TR, we're going to plug it into the top equation. And there's the top equation. We're going to substitute in TR right here. That goes there. So there it is. So we have TLs here. We can factor them out. And we have TL. This big thing in the square brackets is just a number. To solve for TL, we divide by that number. And we get 50.77 pounds. That's TL. And we have an expression for TR as a function of TL. We can use that expression to get TL, about 77.8 pounds. Of course, we should check this. So this is our expression in the vertical direction. We're going to plug in TR and TL, which we just found. There it is. And it turns out to be 100 pounds. This part is 32.63. This part is 67.37. That's 100 pounds. The right one, as you might expect, is doing more to hold up the stoplight. The horizontal forces balance as well. TR cosine 60. This is the horizontal direction, and we can stick in the values of the tensions, and they're both 38.9 pounds. We can see this with the force diagram. It's a good idea to look at the force diagram. There it is. The upward forces are 100 pounds, and the sideways forces balance. The upward forces of the tension are holding up the stoplight. The tensions in the cable, here are the answers, 77.8 and 50.8. A good force diagram will allow you to see what's going on so it makes sense. Invest the time to draw a good force diagram so you can see what's going on rather than just look at a bunch of math on the page. As a reminder, here's what we started with. We started with TR and TL and a stoplight hanging there. Those are the angles. We used trigonometry to get the components. We wrote force equations. Now we had 2 equations and 2 unknowns. We did a bunch of algebra and were careful, and we got the right answer. The last part of this series on manipulating vectors involves conservation of momentum.